Hey Multi, we're doing section 13.3 arc length.
And continue our work with vector-valued functions, today we're going to take a look at arc length. So our goal by the end of this lesson is to be able to calculate the arc length of a vector-valued function over a given interval, as well as reparameterize a vector-valued function in terms of arc length, as opposed to time. So let's start with arc length. So suppose that the curve is defined by the vector function r of t, which has components f of t, g of t, and h of t, where f prime, g prime, and h prime are all continuous. Okay, so this is saying that the component functions all have continuous first-order derivatives. Then the arc length is the definite integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. Okay, so this should look pretty familiar to us because we did define arc length in single variable calculus. Okay, but we need now a third component because we have a z component to deal with as well. Now the square root also should make sense because arc length is essentially a distance. Okay, so this is really just a manipulation of the distance formula. Now this may look a little more familiar to you parametrically, okay, because a vector valued function is just a parametrically defined function. Okay, so this expression of the arc length might look more familiar to you, where f prime is represented as dx dt squared. Okay, so the derivative of the x component with respect to t, and then dy dt and dz dt as well. Okay, so this is just relating and putting it in a form that might be more familiar to us with our work through single variable calculus. Okay, so what are we calculating when we're calculating the arc length? We're calculating the distance from t equals a to t equals b. So the point defined by the vector valued function when t equals a, and the point defined when t equals b. We're finding the distance that we travel along the space curve in that time interval. Okay, so the length of the red line that I drew is what we're calculating with this computation. Now there's a better way to write this out using better notation that we've worked with so far through this course. Okay, so we can define arc length as the integral from a to b of the magnitude of r prime of t dt. Okay, so the magnitude of the tangent vector is what we're going to integrate. And this makes sense because if we think about what the tangent vector looks like, r prime of t, that's f prime of t, g prime of t, and h prime of t. And finding the magnitude of that vector quantity would just give us this expression here. Okay. Now as far as relating it to a little bit of a real-world example, we haven't defined motion in space with vector-valued functions yet, but we will get to that point. R prime of t being the tangent vector represents the velocity vector. So the magnitude of velocity is speed. Okay, so essentially we're integrating speed over a given time interval, which speed times time is distance. Okay, so that's why this is the definition of arc length of a vector-valued function. Okay, so just give us a little bit of a different perspective. So let's look at calculating the arc length of the vector-valued function r of t, which is 3 cos t, 3 sin t, 4t, from 0 to pi. So first we have to start by finding r prime of t, our tangent vector. So that's negative 3 sin t, 3 cos t, and 4. Then the magnitude of our tangent vector is the square root of 9 sine squared t plus 9 cos squared t plus 16, which is just the square root of 9 plus 16 using the Pythagorean identity simplification. That sine squared plus cos squared is 1. So we get the square root of 25, which is just 5. So then to calculate the arc length from 0 to pi, we're going to integrate from 0 to pi 5 dt, which is a simple enough calculation. So we get 5t evaluated from 0 to pi. So we get 5 pi as our arc length. Okay? So that's the computation to calculate the arc length over a given interval. So now what we want to do is we want to create a function out of the arc length so that we can relate arc length to time. Okay, so that's what this is doing right here. So s of t, s standing for arc length, a variable that we've used before, right? Most notably s equals theta r, is equal to the integral from a to t of r prime of u, the magnitude of that vector quantity, du. Now, notice that the integrand is u now because t the variable is part of the bound of integration. Okay, so we have to use a dummy variable. The variables can't match here. Okay. So S of t represents the length of the space curve from some fixed point when t equals a to some arbitrary point when t is equal to t. Okay, so basically it's a way to create a function that allows us to calculate the arc length given a fixed point to start at, find the arc length to any point on the space curve. Okay, so that's essentially what we're doing when we're creating the arc length function. Okay, so here's our fixed point, and then t being any possible real number, okay, we would be able to calculate the arc length to that t value, or to that vector and point defined by that t value. Okay, now again, the reason for doing so is that we can then use that definition to find t, time, as a function of s. So instead of having r of t, now I know it says r of t of s because right now we're assuming time is a function of arc length. And what we can do is instead of r of t, the way we've defined the vector value function now, we can define it as r of s, which is a vector value function in terms of arc length as opposed to time. And that's what we're referring to when we say we're reparameterizing the vector value function or the space curve. Okay, we're eliminating the t and replacing it with an s. Okay, so let's do that. Let's reparameterize this vector value function 3 cos t, 3 sin t, 4t, where we're starting at t equals 0 and going in the direction of increasing t. Okay, so we're going to define the vector, the arc length function, s, which is going to be equal from 0 to t, the integral from 0 to t, of the magnitude of r prime of t, which we know is just 5 dt, right? We did that work. It's the same vector value function that we used previously. And actually, I need to be careful. Can't use t here. Okay, so I got to use u, okay, because t is in our bounds of integration. Okay, so I'm okay making that mistake because it allows us to talk about it. So then the arc length s is equal to 5u evaluated from 0 to t. So s is equal to 5t. So arc length, the relationship between arc length and time right now is that the arc length is equal to 5 times the time. But what we want is we want t as a function of s, so t is equal to s over 5. So what that allows us to do then is to go back into our vector valued function and replace all our t's with s over 5. Okay, so there's our new vector valued function defined in terms of arc length as opposed to time. Now, most of you are probably looking at this going like, why would we want to do this, right? Is this more just an exercise in doing algebra than anything else? And the answer is no. There is an actual motivation behind defining the vector valued function in terms of arc length as opposed to time. So let's look at that in the next example. And I'm just going to copy this because I know I need it on the next slide. So why take a perfectly well-defined vector valued function in terms of t and go through all of this extra work to define it in terms of the arc length s? So the situation that I'll ask you to think about as motivation is giving directions to your house. Think about giving directions to a group of people and telling them to go 5 minutes down the road and then make a right-hand turn. Hey, you're not guaranteeing that every person that you tell the directions to is going to make the same right-hand turn because the distance that they've traveled in 5 minutes might be different for everyone. Whereas if you tell someone go 2 miles down the road and then make a right-hand turn, you're guaranteeing that everyone will make the same right-hand turn because 2 miles will not change. Okay, so that's the idea of redefining a vector valued function in terms of arc length as opposed to time. Okay, based on how we want to define the situation that we're working with. Okay, so the question that can be asked is, where on the curve r of t are we after traveling for a distance of 5 pi over 3? So here they're not telling us to travel for 10 seconds and figure out how far we went. Here they're saying you've went a distance of 5 pi over 3 on the curve. Right? And in the situation that I just gave you, it's a real situation that we can come across, right? Where we know the distance that we've traveled and we want to know where on the space curve we are. So it didn't copyright. So the vector valued function r of s is 3 cosine of s over 5, 3 sine s over 5, and 4s over 5. Okay, so now, instead of having to go through all this work to find the time when you're 5 pi over 3 along the curve, we can just plug the distance directly into the vector valued function. So we can calculate r of 5 pi over 3, which is 3 cosine of pi over 3, 3 sine pi over 3, and 4 pi over 3. So simplifying with the trig ratios that we know, this would be, let's see, 3 over 2, 3 rad 3 over 2, and 4 pi over 3. So this is the point defined by this vector that we'd be at on the space curve after traveling a distance of 5 pi over 3. Okay, so that's one of the motivations of why we reparameterize vector valued functions in terms of arc length as opposed to time. Okay, it doesn't happen often, okay, but there are situations where we must do so. And we're going to look at that as we proceed through this course, okay, in situations where it makes more sense to talk in terms of distance as opposed to time. All right, so write down any questions that you have. All right, we'll answer them as part of our discussion and then proceed into the problem set. Enjoy the rest of the day, and I'll see everyone in class.